In this lesson, we cover the theory of operation of stepper motors. Now, if your focus is software, some of this is not completely necessary to know, but in my career, I've always found it useful to understand things in more depth than necessary, and I think it makes my work more enjoyable. You can see the topics here, which I'll go through quickly. We'll start with stepper motor basics. Then we'll get into the different designs of stepper motors. Here I compare the operation of a stepper motor to a person climbing a ladder. Then we go into the actual operation of stepper motors. Here is where some software comes into play as we talk about the signal patterns needed to drive a stepper motor. Then we'll get into prompts or questions and my take on them, and we finish with a brief summary. So let's start with the basics. So what makes stepper motors unique is that they move in precise and predictable discrete steps. Compare this to other motors which move smoothly in a continuous way. The stepper motor we're using for this course, which has this part number, has 2048 steps per revolution. This includes the effects of gearing, which I'll discuss in the next slide. Often you want lots of steps per revolution, as this gives you fine control over what you're controlling. Stepper motors are controlled by signals, typically 4, sent over wires, which cause the motor to move step by step forward or back. These signals come from GPIOs, which are controlled by your software. The nice thing about stepper motors is your software can know the motor position by keeping track of how many steps were performed in either direction. This makes stepper motors great for positional control. This is known as open loop control, as there is no feedback of motor position to the software. The software just assumes the motor is moving as commanded. With closed loop control, there is some measurement device to tell the software the true position of the motor. So a potential problem is if the load on the stepper motor is too high, or you could say the motor is too weak, or maybe there's some other mechanical problem. What can happen is the motor can start to slip steps, meaning it is being told to move, but it can't. The software will be unaware of this, and it will then be out of sync with the actual motor position. So do you worry about this? Well, it depends on what the system is doing. Take the case of a printer, for example. The stepper motors should only slip if there is a mechanical fault. And the designers might say, well, in that case, the printer's broken and I don't really care about slipping steps. However, if the product has some safety aspect to it, you might need to detect slip, and so that your software can respond to that. And then there's the question of startup. In many cases, your software needs to know the current position of the motor or hardware, or get the motor or hardware into some known position. I call that process calibration, and here are a few ways to do it. One is you could have a limit switch somewhere in the system. And here's a picture of a typical limit switch. And the idea is when the hardware reaches some known position, it pushes this lever down. And the switch would be connected to a GPIO on your MCU. So after power up, you run the motor until the switch closes, and now you know the position of the hardware. Another thing you could do is put an absolute rotary encoder on the motor or some rotating piece of the hardware. And the software can then read that rotary encoder and know the position of the hardware. And finally, another way is to simply run the stepper motor for some period of time, knowing it will hit a hard physical limit. When it hits that hard limit, the motor will simply skip steps until the software stops trying to move it. Now, the software knows the physical position of the hardware, since it knows it has run it long enough to hit that limit. So this system might sound crude, but it is simple and it works. Now we'll get a little bit into the physical design. There are different stepper motor designs, but they all use the same technique of moving the motor step by step using electromagnetism. I think of a stepper motor as climbing a ladder. You go step by step and you use your hands and feet in a coordinated way. And there are different hand and feet patterns of motion you can use. We'll see the same applies to stepper motors. So the number of steps per revolution is based on the physical design of the motor itself plus any gearing. So the motor we're using has 32 steps per revolution internally, plus it has a gear reduction of 64 to 1, meaning the internal motor must rotate 64 times to get one external rotation. So 32 times 64 gives 2,048 steps per revolution. Now, one thing I want to mention is that there are two types of stepper motors from an electrical viewpoint, unipolar and bipolar. I won't go into it, but bipolar requires more complex driver circuitry, but it gives about 30% more torque. Unipolar has simpler driver circuitry, and that's what we are going to use for the course project. So here are a series of pictures that show how stepper motors work. We are looking at the motors from the end, and as you go from left to right, the pictures become more realistic. And at the bottom of the slide is the URLs where I got these pictures. So this first picture is not very realistic, but it gives you the basic idea. And in this picture, we show a battery, which is like a power source, and we have 4 switches that you can turn off and on. When you close a switch, the corresponding stator, which is this part, acts as an electromagnet and becomes magnetized. By the way, stator stands for stationary. The rotor, which is this part here, has permanent magnets, and when the stator becomes magnetic, it will attract a pole on the rotor. Each end of this rotor is called a pole, and it will attract it and cause it to rotate to line up with the stator. And then what you can do is open the switch and close another switch and cause it to rotate to the next stator, and so on. Now in our project, instead of having manual switches, we have the MCU and GPIOs doing that function. Now this first picture would only have 4 steps per revolution. A more realistic motor is the second one, and you'll see that the stators and rotor poles have teeth, which are sort of like mini stators and mini poles, and so you move one tooth at a time. So this motor would have, I think, 24 steps per revolution. This third picture is an actual photograph of a real motor, and you can see more teeth and more stators, and this will give you even more steps per revolution. Now, I talked about gearing before. This last picture is a photo from a YouTube video where someone took apart one of the motors we're using for this class, and the first thing that you see is this gear reduction. This little gear in the center is the actual motor, and then it drives this gear, and which drives this gear, and so forth. And in the end, you get a 64 times gear reduction, which increases the number of steps per revolution by 64, as we did that calculation just a second ago. So now we're getting to the part of the stepper motor operation that involves the software. So a pattern is a set of signal values that is sent to the motor to energize stator coils to create magnetic forces that will turn the motor to the next step. And typically there are 4 signals in the pattern using 4 GPIO outputs. Now I include this picture again just to remind you how these signals are used to create the magnetic forces in the motor. So a pattern sequence is used to drive motion. The table below, near the bottom of this slide, shows these pattern sequences, and we'll talk about that in just a moment. But for now, I just want to point out that there are 4 or 8 patterns in each sequence. So you just keep sending the sequence over and over again to rotate the motor. So going back to my ladder analogy, these pattern sequences are like how you move your hands and feet to climb a ladder. And if a pattern sequence is sent in reverse order, the motor turns in the reverse direction. Again, it's a little bit like a ladder. Now, half steps can be achieved by holding the rotor between 2 step points using a specially designed pattern sequence. So this doubles the number of steps per revolution. You can take this further and do micro steps. In this case, you vary the electrical power for each stator to more precisely control the position of the rotor between steps. And in this way, you can approximate continuous motion. To go back to the ladder analogy, this would be like sort of freezing your muscles at any time as you move from one step to another. It's not easy, but it's possible. So for this course, we support 3 pattern sequences. First, there is the normal full step sequence. Then there is something called wave drive, which is also a full step sequence, but it uses less power, but also results in less torque. And then finally, there is a half step sequence. So this table shows the pattern sequences. The rows represent the 4 wires that we're driving. And these columns for each pattern show the steps in the sequence. And then these dots show which signals or which coils are energized at each step in the sequence. Now over here, I show this picture to show a pattern sequence in operation. It's a little animated GIF, which I think is pretty clever. And I believe it came from Wikipedia. And now this diagram, I think, is showing wave drive, because looking at this, there's just one stator energized at a time. Now this slide gets a little into the electronics. You really don't need to understand this stuff, but I'll try to explain it so hopefully you get the idea even without much electronics background. So for each GPIO and each stepper motor coil, we have one of these circuits. And you can see the stepper motor coil. It's this right here. There's 5 volts on the top, and on the bottom of the coil, it's connected to this little triangle thing here, which is a driver. And it acts like a switch that's controlled by the GPIO coming in here. So the driver's output will be forced to 0 volts when it is turned on by the GPIO, meaning your software. And when this is done, we now have 5 volts across this coil, and current will flow and the coil is on. That's the basic operation. Now, this thing here is an LED and a resistor, and it doesn't serve any other purpose other than to show you that the coil is on. I will occasionally glance at these when I'm doing something just to be certain that it is running. Now this dotted line means that the things inside it are inside the driver chip, and so there is this driver circuit here, which I described. And there's also this diode, which is an electronic thing needed when you drive a coil, and I won't go into it. So that's it. There are 7 of these circuits in the chip, but we only need 4 of them. Now, a few other things. For micro-stepping, you don't just turn the coils on and off. Instead, you control them precisely to get the rotor to turn gradually between steps. Typically, you use a pulse width modulated signal, which is PWM, and MCUs have hardware that support generating these kind of signals. That's all I'm going to say about micro-stepping in this course. We won't be using it. For a bipolar stepper motor, an H bridge is needed to reverse the flow of current in motor coils. So you would need a more sophisticated circuit than the one I show here. And as I mentioned previously, bipolar stepper motors do give you more torque. That's their advantage. And then finally, what I should say is that this circuit above is pretty basic. There are more sophisticated stepper motor chips that provide the H bridge. They allow you to do current control. They will detect overload, current overload, and do other features that are needed in many real-world applications. On this slide, I cover a few more topics on stepper motors. You can go into a lot of depth in these topics, and my goal is just to introduce you to the ideas. So first, torque on a stepper motor decreases as the speed, or steps per second, is increased. And this provides a limit to the speed of a stepper motor. So this chart shows it. The y-axis here is torque that the stepper motor is able to provide, and the x-axis is steps per second. So at 0 speed, the torque is maximum, and as the speed increases, the torque eventually goes down to 0. Now there are two curves here. This higher curve, which is called the pull-out torque, is how much torque the motor can provide while the motor is rotating. And this curve is called the pull-in torque, and it's how much torque the motor can provide while starting from a dead stop at a particular speed. The holding torque, which is shown here, is how much force is needed to forcibly rotate the motor when the coils are energized but the motor is not moving. Now, they call this region here the start-stop region because at these speeds and torques, the motor can be started and stopped at will. So how much torque do you need? Well, that depends on the load, and there are several factors. One is dynamic load. If a stepper is connected to a load with a lot of mass, it takes torque to accelerate it. You might need to control the acceleration, for example, do slow starts and slow stops. Here is the basic formula from physics. Torque is equal to the rotational inertia times the angular acceleration. There's also different kinds of friction. One type is called dry friction, and of course this friction occurs when things are rubbing together. There is static dry friction, which applies when you're trying to get something to start moving from a stop. And then there is kinetic friction, which applies when something is already moving and you need to keep it moving. So normally the static friction is higher. It takes more energy to get something to start moving than to keep it moving. And then there is viscous friction, and this is the kind of friction that increases as the speed increases. So in general, you need to add all these together, and that is the amount of torque you're going to need from your stepper motor. The final thing I wanted to mention is that stepper motors that have gears will have some backlash, what's known as backlash, when the load changes direction. And it's just some looseness in the gears. Some people would call it slop. And this backlash occurs when you or can occur when you change the direction of the rotation. It really depends on what kind of forces are being applied to the motor. I wouldn't probably mention this, except it shows up in the demo. Generally, the cheaper the motor, the cheaper the gears, and the worse the backlash. And keep in mind, I'm working with $2 motors here. Here are the prompts for this video lesson. I'll just pause a moment and then go through them and give my take. And by the way, some of these questions are pretty open-ended. If you have thoughts on them, I encourage you to leave comments on the video. Name some advantages and disadvantages of the run against a hard limit method to calibrate the stepper motor position. And this would be calibration, for instance, on power up. Well, some advantages are you may need no extra hardware. For example, you don't have to buy a limit switch. Another advantage is the procedure might give a very practical reference position for your device. For example, if you have a device that's closing and opening a door, if the hard limit is a door being fully closed, that's a useful position to use as a reference. Some disadvantages, one is the device has to be mechanically strong enough to force the stepper motor to slip steps. You don't want to tear apart your device. The procedure must not cause overheating the motor. I'm not sure how much of an issue that is, but it's something I would look into. There is no confirmation that you've actually reached the end position. So if there is a mechanical fault in the device, you wouldn't know that. Again, whether that's important or not depends a little bit on your application. And finally, the procedure might be noisy because you hear this thing hit the hard limit, and then the stepper motor is going to vibrate, I think, as it's skipping steps. What might be issues with quickly and precisely calibrating a stepper motor that uses the limit switch technique? What software solutions can you think of? Well, what I thought of is you want to move the motor fast to quickly get to the limit switch, but then you might overrun that position after the switch is closed. In other words, you ran the motor a little bit longer than you needed to. So in software, what maybe you could do is you could quickly move to the limit switch until you detect it being closed. But then after that, you would slowly move back until it opens and then slowly move forward to get the exact step where the switch closes. Why is coil current sometimes reduced, if the circuitry supports it, when a motor is being stopped and being held in place? What are the factors involved in doing this? Well, coil current would be reduced to reduce power consumption in motor heating. So reducing the current reduces the holding torque. The main issue is how much torque is needed to hold the motor and whatever it's connected to in a stop position. And this can depend a lot on your application. But this current might be, and in many times I think would be, less than the torque needed to turn the motor, as there's no need to overcome friction. Your stepper motor is slipping steps and getting out of sync with the software. What are possible reasons? Well, I list several here. The first one is a software bug. Now, I say just kidding, but I'm really not just kidding, because sometimes you'll think, there's a problem in the hardware, and no, it's actually a problem in your software. But let's go to some more interesting reasons. One is you're running the motor too fast. It reduces the torque and it just starts to slip. Another is the load has a lot of inertia and you're trying to accelerate it too fast. And so you need to control the acceleration on starts and stops. Do slow starts and slow stops. Another thing is there could be problems with the stepper power supply, and not enough current is being provided in those stepper motor coils. And another one is that the stepper motor is just undersized. You bought a stepper motor and it really does not have enough power for the application. So here's a summary of this video lesson. Stepper motors use electromagnetism to move the motor step by step. This is done by generating currents in the motor's coils to cause the rotor to move to the next step. Rotation is controlled by the MCU by sending a sequence of signals, normally using 4 GPIOs, to control the motor currents. Software can know the motor position by keeping track of how many steps were performed. Often, some procedure is needed to determine the current motor or hardware position when the system starts up. Torque decreases as rotational speed increases. And finally, a motor might slip steps if there is insufficient torque for the load. In this case, the software no longer knows the true motor position. Well, that's it for the video lesson on stepper motor theory of operation. The next lesson will be about implementing a stepper motor driver for STM32. Thanks for watching.